we're going to see how to apply Ampere's law in a couple of situations, just like we were doing with Gauss's law. It shouldn't surprise you that it only works for certain symmetries, so I'm going to set up some of those so you can see how it works. So we're going to first start again with a long wire, but now we're going to sort of zoom inside that wire to say what is the magnetic field at some point inside the wire, like at that point. So the question is, we have current that's uniformly spread out through this wire. We could still have 3 amps of current, for example. And the question is, what is the magnetic field? So find the magnetic field inside the wire, a distance r from the center. Okay, so using Ampere's law, if it's a very long wire, we're going to hope that we can use that same symmetry. So we're going to say B dot dl is equal to mu naught I enclosed. And just like Gauss's law, the trick here is to draw the right loop. In this case, we want, again, an Amperian loop. Right? This is what happens at the loop. This is what's inside. So if we look at this to find the loop, what we're interested in is a loop that encloses the point of interest. So it would enclose this point, and we want it to be symmetric. So that would be our loop. And we'll kind of say that'll be our dl, will be some little element along here. Right? And our magnetic field we can recognize because of using our right-hand rule, where we take our thumb in the direction of the current, we take our fingers to curl around, that our magnetic field is going to be in this same direction. This would be our magnetic field. That would be the direction of B, circling around. And so we can say that B dot dl is just going to be the size of B times dl times the cosine of the angle between them, but they're pointed in the same direction. So the way I've set this up, the dl is in the same direction as the b everywhere along the way, so that's cosine of 0. So the left-hand side of the equation here just becomes integral of b dl is equal to then mu naught I enclosed. That's the right-hand side. So I was focusing on the left-hand side of the equation. Now I can look at the right-hand side of the equation. Now the current inside, we can tell that we don't include all of the 3 amps inside. We only include some of it. And in fact, the amount we include is going to depend on this area. In fact, we can talk about a density, as we have already with currents. We can say our current density, J, is current per area, right? That we go through. So the current density is the same everywhere, but we can say that it would be the total current, that would be the 3 amps over, say this whole thing has a radius of capital R of pi r squared, or we could also say this J, you would have the same density of current in that area, so you would say this J is also equal to the I enclosed, however much is inside, over the area which enclosed, which is pi r squared, little r squared. And so we can equate these two, because it's the same current density. The total current over the total area is equal to the current that's inside that area divided by this green area. And so equating those, we can then say that I enclosed over pi little r squared, that's the radius that I've now covered up, that's this little r, is equal to 3 amps, our total current, over pi capital R squared. The pi's go away. The I enclosed is equal to 3 amps little r squared times big R squared. And so we can substitute that in there, and we're basically almost done now. This magnetic field, I'm arguing, is a constant because it's the same distance from the center. That's why we want to make this loop exactly symmetric on the center, so that we can say it's got the same amount. Doesn't matter whether you're here at this point or you're on the back side. Everything looks the same because this is symmetric. It's cylindrically symmetric. So this B is constant value. The magnitude is, the direction's changing, but this is just the magnitude. So I've got B integral dl is equal to mu naught 3 amps, or whatever current we have, little r squared over capital R squared, and this is just the length of the loop, so length of the loop of our Amperian loop. So in this case, it's going to be 2 pi times the radius of the loop, which would be little r. So I've got B times 2 pi r is equal to mu naught 3 amps r squared over capital R squared. Big R is the bigger radius of this. So this magnetic field just becomes mu naught times 3 amps r squared over 2 pi little r capital R squared. That cancels one of these out, and it's mu naught 3 amps all over 2 pi r squared times r. And all of this is just a constant. It depends on how much current and the size of the wire. So if we look at this, the magnetic field increases with our radius. But note that when little r is equal to big R, in other words, when we're on the edge, right, we get B is equal to mu naught times 3 amps over 2 pi now over R, which is what we would get if we were looking at the magnetic field outside the magnetic field of a long wire at this point. So in general, so that checks out. That's a nice thing. So in general, the magnetic field as a function of little r, distance from the center, according to this expression, when we have a little r of 0, we've got 0 magnetic field. That makes sense. No currents inside. And then it goes linearly, that's this expression, up to when little r equals big R. And then afterwards, outside, for a long straight wire, we have B is equal to mu naught, the total current, over 2 pi, the radius. So in fact, as 1 over R. In other words, it drops off as we get further away. So that makes some sense. I think we get far enough away, this magnetic field heads off to 0. We don't notice the influence. Okay, so let's do a second example. The second example is with something called a solenoid. And basically, it is a wire that is wrapped around a cylinder. So we have a cylinder like this, and we take our wire, and we kind of, it comes up like that, up like that, up like that, back, and so forth. Okay. So we have current. Let's say we've got current going like this. So the current goes down like that. Comes up on the back side, it goes up. So this is the direction of the current. And so first we can ask the direction of the magnetic field. And so if we take our thumb, it's sort of pointing down on our right hand, pointing down along the wire in front of our screen, then when the fingers get sort of towards the inside, the magnetic field right around any one of these is going to kind of loop like that, right? And on the inside, it's going to go like this, and then this one is going to loop like that, like that. And when we blow this up, right, this is coming on this side, it's coming out of the page, and then on this side it's going into the page. So on these side points right here, like right there, it's going to cancel out, but what we can see is that the outside and inside are going to add together, and so overall what we do is we get a magnetic field inside the tube, sort of like this, that points that way. It comes out of the tube and circles around and goes like that. And that should look vaguely familiar because that's the kind of setup we had when we had a permanent magnet, right? We said that the magnetic field sort of pointed like this, if this is our south pole and this is our north pole. So one way to think about a permanent magnet is that it's made up of lots of little loops. It's not big wires like this, but it's made up of little tiny current loops that are sort of lined up, and those current loops actually have to do with the rotation of the spin, actually, of unpaired electrons that are inside the material. Okay, so that's just an aside. This looks like this setup, but we don't know the current in that setup, so we're not going to focus on that anymore. We're really going to just look at the solenoid. And what we want to do is find the magnetic field due to a long, but not infinitely long, this is sort of an approximation, a long solenoid. So that's the idea. It's fairly long. And what we're going to do is say we're going to set up our Amperian loop. And this is a not expected Amperian loop. So what we're going to do is still use Ampere's law, and the trick is to find the Amperian loop. So we want it to follow along the direction of the magnetic field. So I make it along the direction there. And then I'm going to make it come through, sort of think of those as dotted, and then it comes to the outside. Make it really long, and then like this, okay? So this is our Amperian loop. These are our DLs on the Amperian loop. I'll draw those in here as a DL along all these different sides, right? Okay, so it's a rectangle, which is not expected really with this symmetry. And this is one of those, you sort of have to know where you're going to kind of pick the loop that you would use, but when you see how this works, hopefully you'll say, oh, okay, that makes sense. So let's look at what we're doing. So we're going to look at this integral of B dot dl is equal to mu naught, the current enclosed in our loop. So we actually do have the current enclosed in our loop. Well, in this drawing, I actually don't have any current. Let's say that I've got one coming down like this. I could have more wires, right? So we count up basically however many wires we've got in there times the current. So that gives us our current enclosed. But before I looked at this right-hand side, I want to pay attention to this because we've got to do this on all of the sides. So we've got to do this on side 1, side 2, side 3, and side 4. Okay? So this becomes now an integral because we've got to go around the whole loop. In this case, it's a rectangle. So this means the integral of B dot dl for 1 plus the integral of B dot dl for 2 plus the integral of B dot dl for 3 plus integral of B dot dl for 4, which doesn't seem like I'm making it any simpler. This seems kind of complicated at this point. And some of it is, but the first thing to notice is that from the way I've drawn things is that notice that on side 2, the magnetic field is going in this direction and dl is in this direction, and that's 90 degrees. So for side 2, I've got B times dl, and B is changing because it's stronger here, weaker here, and weaker even further out because we're further away. But that's times the cosine of 90 degrees. And cosine of 90 degrees is 0. So, because of the direction of the magnetic field and the loop that we drew, this B dot dl, even though the magnetic field is not 0, the dot product is 0 because we've got 90 degrees between these two vectors. Right? This is the direction of B. This is the direction of dl. So that's 90 degrees right there. This gives me a 0. Same argument for side 4, of course. So now I only have to do 2 of them. And side 1 is pretty easy. dl is in the same direction as B, right? And by some symmetry, we could say, hey, the magnetic field, if we're in the middle and it's a very long tube, the magnetic field along this little piece of wire is basically going to be constant. So I can say this is B along 1 dl plus now B3. So the thing about 3 is, this is kind of a cheat. We say we can make this loop as big as we want. So what we do is we say this is far enough away that our magnetic field is headed to 0. Okay, we just get really far away. And so we send this B3.dl. We just say that's 0. Okay, so this is an approximation. Okay, works pretty well though. So all of this, all 4 of these sides just come down to the side 1. So this becomes b times the integral of dl, because they're in the same direction, so the angle between them is 0. So this just becomes b times the length of side 1. So let me draw that in L1. It's not a very long length, but there it is. And that's equal to mu naught times the current that's enclosed. And now typically what we do with solenoids is we describe them by a little n, that is the number of loops per length. Okay, so the idea is that you're turning this, when you build this, you actually can put it on, well, the simple one is on a drill, but you can put it on a lathe or something, and you turn the cylinder and you say how many loops per centimeter, for example, or how many loops per meter. Or if you think of a slinky that you can stretch, you can change the number of loops per meter. So the number of loops per length is given there. And so then the current enclosed would just be, right, the current in the loops, whatever this initial I is, times the number of loops per length times this length that's enclosed, that encloses it. That's how many. So like if we have here 3 loops per centimeter, and L1 is 1 centimeter, then we'd have 3 times whatever our current was. If our current was 2 amps, we'd do 3 times 2, and that would be 6. So it just depends on what numbers there are, but this is the most general expression for the current enclosed. And so then we get B times L1 is equal to mu naught I in L1. And the L1s go away, which is convenient. And the magnetic field, which is inside a solenoid, points along the axis, is equal to mu naught I times N, where this N is the number of loops per length, usually per meter. I mean, in our units, if we want it in Tesla, that would be number of loops per meter. And so that will give us an expression for the magnetic field that's inside this, and it points in that direction up the center of the solenoid.